everybody, welcome to section 4.9, antiderivatives. Today we're going to be talking about the opposite of derivatives, antiderivatives. So we're going to be working backwards. Now the better you are at taking derivatives, the easier this section will come to you, because we're going to be given the final result and we have to try to determine what function this function is the derivative of. So for example, if I said given the function f of x equals 3x squared, can you find another function whose derivative is 3x squared? Well, again, depending on how comfortable you are with taking your derivatives, you may recognize that the function we're looking for is x cubed, right? Reason, the derivative of x cubed, we bring the power out front, leave the variable alone, and drop the power by 1. So g of x equals x cubed is a function whose derivative is 3x squared. But the question is this the only function whose derivative is 3x squared? What about g of x is equal to x cubed plus 7? The derivative of x cubed plus 7 is 3x squared plus 0. So the derivative of x cubed is 3x squared. The derivative of x cubed plus 7, what about, is also 3x squared. What about x cubed minus 600? What is the derivative? The derivative of x cubed minus 600 is also 3x squared. So when we're working backwards, we have a different scenario than when we're working forwards. Taking a function and finding its derivative, we get one answer, but given a function and looking for its antiderivative or working backwards, we can get many answers. Actually, this number in the end can be anything. What we do is we say g of x is equal to x cubed plus any constant c. So c can be any constant. Notice that the input variable is x, so the variable is x, and this is a constant, so for any constant. So this is called the general antiderivative of 3x squared. Oops, get some blank paper here. Bear with me, on my blank paper. We call g of x, which is the function x cubed plus any constant c, the general antiderivative of the function f of x equals 3x squared. Answers like g of x equals x cubed minus 600 or g of x equals x cubed plus 7 are called particular antiderivatives. They're part of this infinite collection of functions, or this family of functions, g of x equals x cubed plus c. So let me write that here. We call the answers g of x equals x cubed plus 7 and g of x equals x cubed minus 600 particular solutions, or particular antiderivatives. Right? A particular antiderivative is a specific case of the general antiderivative, and in order to find these values, c can actually be anything unless they provide you with further information that helps us find that value of c. To find a particular antiderivative, for a given function, you need to be provided with additional information. And we'll see that in an example shortly. Okay, so continuing, let's try another example. Find the general antiderivative of the function f of x equals 4x cubed minus 8x. Answer, I'm going to call the general antiderivative g of x. So I need to find a function whose derivative is 4x cubed. So thinking backwards, we need a function such that when we bring the power out front and drop the power by 1, this is the final result. And this just comes more naturally the more practice you do. So we think about x to the 4th, we bring the power out front, drop the power by 1. That would give me the derivative 4x cubed. Now I have to be a little bit more careful here. The derivative, a function whose derivative is 8x. Well, in order to get a linear function, the power would have to have been 2 originally before we took the derivative, because when we bring the power out front, it would drop the power to the 1 that we don't see here. But then we have to think what constant would go out here, such that when I bring the 2 out front, I get 8. And the answer would be 4. So let's see. Derivative of x to the 4th minus 4x squared would be 4x cubed. Bring the 2 out front, 8x, drop the power by 1. But we're looking for the general antiderivative, so you can't forget the plus c. The plus c is essential. All right, so we talked about particular antiderivatives, so let's look at this case. I say find the antiderivative of f such that g of 1 equals 3. Well, we found the general antiderivative just a second ago. So the general antiderivative, the family of functions whose derivative is 4x cubed minus 8x, is 8 to the x to the 4th minus 4x squared plus c. So this is the additional piece of information that we need to find the particular antiderivative. What that's going to do is tell us the value of c that this problem is looking for. This tells me when I stick 1 into the general antiderivative, the output should be 3. So if I stick 1 in everywhere I see x, I get 1 to the 4th minus 4 times 1 squared plus c, and the result should be 3. So now we just do the algebra. 1 to the 4th is 1 minus 4 times 1 squared plus c equals 3. Negative 3 plus c equals 3. Add 3 to both sides, so c equals 6. So this problem was looking for the particular antiderivative from that infinite collection. This is an infinite collection of functions whose derivative is 4x cubed minus 8x. We're looking for the one particular one that satisfies this additional condition. So therefore, my answer would be g of x is equal to x to the 4th minus 4x squared plus 6. We found the value of c. All right, so let's practice taking antiderivatives. Again, this is a lot easier if you are comfortable with derivatives. The more comfortable you are with your derivatives, the better off you will be with your antiderivatives. I'm just trying to look for a nice pointy pen. Here we go. Okay. Oops, that was that one. Okay, so let's look at some functions and find their general antiderivative. The function x. Well, what function has derivative x? Well, when we find derivatives, we reduce the power by 1. So when we're finding antiderivatives, we have to add 1 to the power. Whoops. So that was 1. We added 1 to the power. So x squared would give me a derivative of the form of x. But when I take the derivative and I bring the 2 out front, we don't have a 2 out front here. So I have to include a coefficient that will cancel out with the 2 and force the leading coefficient to be 1. So common sense tells us that that will be 1/2. So the derivative of 1/2 x squared would be x. We bring the 2 out front. 2 times 1/2 will give me the coefficient of 1. We drop the power by 1. But we're looking for general antiderivative, so don't forget to add the constant. So any function of the form 1/2 x squared plus any constant is going to give me x for its derivative. All right, so what if we had x squared? Well, like this, we have to increase the power by 1. When we take derivatives, we decrease the power by 1 for power functions. When we take Antiderivatives, we increase, but then we need a coefficient out front here such that when I bring the 3 out front, it will reduce down to 1. I'm going to add c. So the antiderivative of x squared is 1/3 x cubed plus c. So like we can continue with this pattern. I can do x cubed. And maybe you're seeing this. Hopefully you're seeing this. It would have to be a 4th degree polynomial in order to give me a 4th degree little monomial term here to give me x cubed. But then I would need the 1/4 out front plus c. So in general, if we have a power function, when we took the derivative, we brought the power out front, dropped the power by 1. Here, we're going to add 1 to the power to find the antiderivative, and the coefficient out front will be the reciprocal of the power for any power except for 1. Because if p equals 1, then we're going to get 1 over 0 here, which doesn't work. So as long as the power doesn't equal 1, nope, sorry, -1. Yep, be careful. It doesn't equal -1 because 1 would work. We just did it up here. As long as it doesn't equal -1 because -1 would give us the denominator and the fraction to be 0, which we can't have. So for any power p, to find the antiderivative, we add 1 to the power and we multiply by the reciprocal power out front. So what happens if p was 1? Well, this is 1 over x. What function has derivative 1 over x? Well, this is one of those things that you just have to remember. I think I gave you a sheet of derivatives. If not, I'm going to include it in, with this lecture, I'll give you a sheet of antiderivatives. But the function whose derivative is 1 over x is the natural log function. So for any power except for -1, we add 1 to the power, we take the reciprocal of the power out front. If it's the power is -1, which is equivalent to 1 over x, the derivative is the natural log of x. The antiderivative is the natural log of x, because the derivative of the natural log of x is 1 over x. All right, keep going. Let's do the square root of x. Now remember, just like derivatives, when we're taking antiderivatives, I suggest you turn all radicals into fractions. So we're going to add 1 to the power. The new power will be 3/2. And then we have to put 1 over 3/2 out front, but 1 over 3/2 is equivalent to 2/3. So just take the reciprocal of the new power, and that's what goes out front. So notice here, if I bring the 3/2 out front, multiply it times 2/3, it will give me the needed coefficient of 1. We drop the power by 1. We're down to a power of 1/2. And we add c. So cube roots. Any root can be turned into a power. So the antiderivative of the cube root of x, add 1 to the power, which would be 4/3, and put the reciprocal power out front, 3/4. Now notice when I bring the 4/3 out front times the 3/4, it gives me the needed coefficient of 1, and I'm going to add c. All right, now be really careful here. We have something like this, 1 over x to the 5th. In order to use this rule, we can use this rule right here, as long as we write it as x to a power. So this is x to the -5th power. Now I can apply this rule. I add 1 to the power. -5 plus 1 is -4. And I put the reciprocal out front. So notice now I bring the -4 out front. -4 times -1/4 would give me the needed coefficient of 1. Subtract 1 from the power. It would give me the necessary power of -5. And we're going to add a constant. All right, now be careful with functions like this. That's a 5. E to the x. What function's derivative is e to the x? Well, again, this is one of those tricky ones. It's so simple that students make it harder than it has to be. The function whose derivative is itself is e to the x. The derivative of e to the x is e to the x. So the antiderivative of e to the x is, well, the general antiderivative would be e to the x plus any constant c. So no matter what this constant is, if I take the derivative of e to the x plus c, I get e to the x plus 0, which is what we started with. So let's keep going. All right, keeping this one in mind, what if I have a constant up here? Let's see if we can work backwards. I'm going to do 10x, e to the 10x. Well, here we have to reverse the chain rule in our head. The derivative of e to the 10x is e to the 10x, but because we have something other than just plain old x up here, the chain rule says when I take the derivative of e to the 10x, I get, so if I take the derivative of this guy, remember we want to get just e to the 10x, we get e to the 10x, the derivative of e to anything is just e to the anything times the derivative of that anything. The problem is I don't have the 10 here, so in order to negate this 10, I'm going to throw a 1/10 out front. So the antiderivative of e to the 10x is 1/10 e to the 10x plus the constant. So e to the negative 13x, the antiderivative would be itself. But then we just have to imagine if we take the derivative of this, we're going to have a negative 13 out front. So we have to counteract that with the negative 1/13 plus c. So in general, if we have e to a constant times x, the antiderivative is going to be itself times the reciprocal of the coefficient plus an arbitrary constant. All right, let's take a peek at our trig functions. Just a quick reminder, the derivative of the sine is the cosine. The derivative of the cosine is the negative sine. Right? The derivative of the tangent is the secant squared. The derivative of the cosecant is the cosecant cotangent. The derivative of the secant is the secant tangent. And the derivative of the cotangent is the negative, whoop, don't forget the negatives, hold on, cosecant squared of x. So if a trig function starts with c, its derivative is negative. So the derivative of the cosine is the negative sine, the derivative of the cosecant is the negative cosecant cotangent, and the derivative of the cotangent is the negative cosecant. So in turn, we have, if I start with the sine, what function's derivative is the sine? Well, we work backwards. Here's a function, that's its derivative. So if I go backwards, the antiderivative of the sine is going to be the cosine. Now I have to be careful because when we take the derivative of the cosine, we get the negative sign, but we started with a positive sign, so I have to counteract that. So the antiderivative of the sine is the negative cosine plus c. What function has derivative plain old cosine? The sine. So the antiderivative of the cosine is the positive sine. So you have to be careful here because the derivative of the cosine is the sine. The antiderivative of the cosine is, all right, say that again. The derivative of the cosine is the negative sine, but the antiderivative of the cosine is the positive sign because the derivative of the positive sign is the positive cosine. Right, walking right down that list, if the derivative of the tangent of x is secant squared, then the antiderivative of secant squared is the tangent plus any constant because we're talking about general antiderivatives. And then we know the derivative of the cosecant is the negative cosecant cotangent. So the antiderivative would be the negative cosecant plus c. So the antiderivative of the cosecant cotangent, well, what function's derivative gives me cosecant x, cotangent x? Well, the negative cosecant would. 1, 2, 3, 4. Then we have the secant tangent, right? What function's derivative is secant tangent? Well, it's the secant of x plus c. So the derivative of the secant of x plus any constant is the secant of x times the tangent of x plus 0. And then the last of our trig functions would be cosecant, negative cosecant. So we're just going to do the plain old cosecant of x, cosecant squared, and the function whose derivative is the cosecant squared is the negative cotangent because the derivative of the cotangent is the negative cosecant, so I have to throw the negative here to counteract that, plus c. All right, so notice here we have the antiderivative of the sine and the cosine, but we don't have antiderivatives of the tangent, the cosecant, the cotangent, because those antiderivatives aren't as straightforward. There is no function that we can obviously see whose derivative is the tangent. We know the derivative of the tangent is the secant squared, so the antiderivative of the secant squared is the tangent, but whose function has derivative tangent? Well, I'll tell you, we're going to eventually get to the proof of this, but if we have a function, the tangent of x, the antiderivative of the tangent of x, and I'm just going to tell you what it is the natural log of the secant of x. So I wouldn't expect you to see that, obviously, but it is pretty cool, because if we use, I can show you, let's show, because to check an antiderivative, we just take the derivative. So if you're good with your derivatives, then finding antiderivatives isn't all that hard. So the derivative of the natural log of the secant, we're hoping gives us the tangent. Well, the derivative of the natural log of anything is 1 over that anything times the derivative of that anything. And the derivative of the secant is the secant tangent. So the chain rule says when we take the derivative of the natural log, it's 1 over what's inside times the derivative of what's inside. These cancel, and you just get the tangent. So therefore, the antiderivative of the tangent of x is the natural log of the secant of x, plus any constant. So not all antiderivatives are as obvious as derivatives. Let's see. What else we got? How about, ooh, we did these. This is a good one. 1 over the square root of 1 minus x squared. The square root of 1 over 1 minus x squared. Well, the function whose derivative is 1 over the square root of 1 minus x squared is the inverse sine. Notice this can also be called the arc sine. So your book goes back and forth between the two. The arc sine is an alternate way to write the inverse sine. Right, we also saw that we know the derivative of the arc cosine or the inverse cosine. -1 over the square root of 1 minus x squared would be the inverse cosine of x. So the derivative of the inverse cosine of x is -1 over the square root of 1 minus x squared. So therefore the antiderivative of -1 over the square root of 1 minus x squared is the inverse cosine, or the arc cosine of x. And then we also saw that the derivative of the inverse tangent was 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared would be the arc tangent of x, or the inverse tangent of x, same thing. So we did last time, just a reminder, I did it on the last page, e to the x would be e to the x plus c. But what if I had something like 2 to the x? What function's derivative is 2 to the x? Again, this comes down to, we're looking for a function whose derivative is 2 to the x. Well, we know the derivative of 2 to the x is 2 to the x times the natural log of 2. So the antiderivative of 2 to the x natural log of 2 would give me 2 to the x. Right, but I have to get rid of this guy. So what we do here is we keep the function, any exponential function's derivative is itself with a little bit of tweaking. If I take the derivative of 2 to the x plus c, I get 2 to the x times the natural log of 2, like we did just right here. So in order to counteract that natural log of 2, I have to throw the reciprocal out front. So the antiderivative of 2 to the x is 2 to the x divided by the natural log of 2 plus c, or 1 over the natural log of 2 times 2 to the x plus c. So if I had 7 to the x power, the antiderivative would be 7 to the x, but then I have to counteract that natural log of 7. So it'd be 1 over the natural log of 7 times 7 to the x. Remember when we took the derivative of 7 to the x, it was 7 to the x times the natural log of 7. When we take the antiderivative, we divide by that coefficient. Right, so in general, for exponential functions where x is your variable, a is your base, the antiderivative is going to be itself with 1 over the natural log of the base out front plus c. So this is if a is greater than 0 and a is not equal to 1. If a is 1, it would just be the constant. So what would we have if a was 1, it was just a constant? If the antiderivative of 1, well, what function's derivative is 1? X plus any constant. For any constant, c, I'll call it any constant a, the antiderivative would be ax plus c. The derivative of negative 23 would be negative 23x plus any constant c. All right, there is your list of functions and antiderivatives. Keep playing with those. Takes lots of practice. Again, the better you are at taking derivatives, the better you will be at taking antiderivatives. So to do, read 4.9 in Stewart. Exercises 1 to 17 odd, 23 to 35 odd, 39 to 45 odd, 49 and 51. And this is, let's see, I just want to see something. And this is XYZ. So you can now work on your 4.10 XYZ homework. All right, guys, don't forget to zoom in if you have questions. Look for my posted office hours each week. If my office hours are not convenient, as always, shoot me an email and we can pick a time that works for both of us. All right, hope everybody's well. Talk to you soon.